Any questions from you, or we try to finish up chapter 5?
I think there was a problem you're going to go back and do.
Yes? Which one? Is it something we did not finish, or?
We didn't finish.
Okay, I don't remember what it was.
On page 404, number 14.
You said 404?
Oh, yeah. Yeah, that's the one. Okay.
You said 404 number?
14.
Number 14.
That's what I have.
Is that okay? Yeah.
Oh.
So cotangent, negative cotangent prime is cosecant squared. Minus 2 e to the x prime is negative 2 e to the x, or e to t, plus a constant c. If I differentiate this side and differentiate this side, I get an identity. The left equals the right. Okay. So I would like to look at section 5.5, which is the last one, and then come back for a few other little things here and there. And this would be the last section. Okay, 5.5, the substitution.
Are you recording?
Yeah. I am. Rule. Okay, why would we ever substitute? Why would we ever think of substituting an expression by some other expression? To make it easier. Otherwise, I will not substitute. I will not change the variable unless changing the variable makes my life easier. Good. That's exactly what we're going to do. We're going to learn how to evaluate definite and indefinite integrals using a substitution whenever makes our life easier. Okay. Now, we can use the we can use a fancy notation, which is fine, but I would like us to establish the basics first and look at an easier route than the sophisticated notation first, and then we can look at other things. Okay, so let's say, bless you. Let's say we start with 28 on page 414, which is e raised to cosine t times sine t dt. First of all, what type of integral is this? There are two types. One is indefinite, which will always give us a function, and the other one is definite, which will always give us a number. Indefinite because there are no limits of integration. So we are starting with indefinite integrals. So I look at this, I see a function, but it's a function that is made out of a product of two functions.
Right.
So this is not a sophisticated way of thinking about it, but I would like us to establish the basics first. I'm looking at these two functions, and I say to myself, sine t, nice. Pure trig function sine t. But when I look at this one, I say, oops. Because e to the x, or e to t, is nice, pure exponential function. But e raised to cosine t is not something that I really like to see. So I'm thinking, if I have a way of removing this sophisticated expression inside e to the x or e to t, then maybe I make my life easier. So I'm going to say, let y be cosine t, because this is what really bothers me. Sine doesn't. E to a variable doesn't. But cosine t inside e to t, it really bothers me. So I look at my substitution and I say, okay, let me see if dy, the differential of y, not the derivative of y, which equals
Negative cosine t, or negative sine t.
not enough. Exactly. That's what I said, specifically not y prime, but the differential of y. If the differential of y is in the problem somehow plus or minus a number, I'm on the right track. I chose the correct substitution. Now I'm going to see if I have dy in the problem. Yeah, if I make a change, multiplying both sides, not both sides, multiplying twice by -1, yes. And I will say, this now becomes dy, and this piece is definitely, exactly. So now the entire integral becomes this. Is this something we can handle better than the previous one?
Yes.
The answer is yes. So we use the substitution. Which substitution? We didn't like cosine inside of e.
What if we don't like what's going on now? I don't understand what happened.
Okay? So I said I didn't, my idea was, if I can get rid of this and change it into e to y,
Yeah.
then I'm going to make my life much easier in determining this integral. So I said, okay, let y be cosine t. dy is the differential of y, which is this. And the question is, do I have this in the problem? Because I cannot make up a sine t if it's not there. I cannot make a dt if it's not there. Well, dt has to be in the problem. So all I had to do is realize that there is a minus in this expression. Fine, I can multiply by -1 twice. And that's not going to change anything. But now I realize that all this piece is indeed dy. And this piece is e to y.
What if that piece wasn't dy?
Then I cannot use the substitution.
Okay.
I have to choose something else. Or I cannot determine this. It's possible. I'm going to choose an integral that we will not be able to, a definite integral, we will not be able to determine. We will be able to approximate, however. So bottom line is, we will not always be able to find the antiderivative of a function. For example, I'll give you, I didn't finish this, so I'm deviating for a second. So if you want to determine the integral of e to x squared dx, you will not be able to find a function whose derivative is e to x squared. A computer algebra system, a software, yes, will be able to give us something. But we will not be able to find a function by hand whose derivative is e to x squared. It doesn't exist. It exists, but not by hand. So we will be able to, if I change this, let's say, between 1 and 4, we will be able to approximate it using the midpoint rule or other rules, right? Dividing the interval into as many intervals as you want and finding the sum of those areas of those rectangles. But we will not be able to find a function whose derivative is e to x squared by hand. Okay, so then coming back here, this I know. Which function prime is e to y?
E to y.
E to y, plus a constant c, of course. Since this is an indefinite integral, I must go back to the variable given in the problem. But that's no problem. So it's e to cosine t plus a constant c. So in a roundabout way, but much easier to determine and calculate, using a substitution helped us determine the integral. So the idea is try to make it as simple as possible. Use a substitution that makes the entire function easier to handle. That's the bottom line. Okay, so now feel free to choose anything you want from the indefinite ones for now. Let's say between 7 and 48 on pages 413, 414. So, for example, 32 caught my eye. So please choose the next one, whatever you want. But in the meantime, we'll do 32. So in 32, we have the integral from sine applied to natural log x divided by x dx. So something looks like a wart. What is it? natural log inside of sine.
Yeah.
That's a big deal. So if I say let y be natural log, if dy, not the derivative, but the differential of y, is good. If this piece is already in the problem plus or minus some constants, I'm on the right track. So it is, here it is dy, and what is this? Sine y. So then the integral now, please, I want to make a remark. You cannot have x and y in the same integral. So if you move from x, everything has to move to y. dy, everything. I don't want to see x again till we are done. Okay? So the integral now is actually,
Sine y times 2y.
it couldn't be easier than this, right? So what function prime is sine y? And the answer will be negative cosine plus a constant c. But I have to go back to the variable given in the problem. And that's not a problem. Negative cosine of natural log x plus a constant c. Now, after you practice these, sometimes you will be able to figure it out without a substitution. So these are not sophisticated problems. Right. Okay, so please choose, or I will.
Will they always have dx or dx and then dy in them?
Remember, the area is the limit of the sum base dx times f of x. So all integrals have to have f of x dx. Width times height, dx times f of x.
It's possible that dx won't be in that notation, it'll be something.
It can be dy, but there is no integral without dx or dt or dy. Yes, there is none. Okay, are we choosing or am I? Which one?
38.
38. I see it. Very good. So in 38, we have the integral from dt divided by cosine squared of t, the square root of 1 plus tangent t. Okay, so these are two different things. Be careful. It's not cosine squared t multiplied by the square root. It's kind of confusing a little bit. Be careful. It's cosine squared t times the square root of 1 plus tangent t.
Minus cosine squared t.
I'm sorry?
Why be cosine squared t?
So
I don't think what's the root of that? Or you could differentiate cosine
it is, so let me think for a second. It's really confusing. So cosine squared should be, so since the power is on cosine, they should have put parentheses and then the power outside. So this is how I understand it as cosine squared t, the square root of 1 plus tangent t. Because it would not make sense. Okay, so now let's think for a moment. You say that you don't like cosine squared, right? I say that I don't like the square root. Not the square root. I don't like 1 plus tangent t under the square root. That's what I don't like. So I think that that's where we should start with. Cosine squared is not a problem. 1 divided by cosine squared can be replaced by secant squared t. So I'm not afraid of 1 over cosine squared. But I do not like the square root of 1 plus a, because I can't simplify it in any way. There's nothing I can do to this. So if I can remove this somehow, and then have 1 over the square root, or maybe use the square root. So I have possibly two options here. Let y be 1 plus tangent t. That could be an option. And then you just chose the problem, so I have no idea which one is better. So, or y is the square root of 1 plus tangent t. We can look at both and say, no, 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 this is not working, and look at the other.
Okay.
Which one would you like to start with? You want to start with the first one, fine. So let's say y equals 1 plus tangent t. As long as dy is in the problem, plus or minus some constant. So dy equals dt, secant squared dt. Okay, it is, because 1 over cosine squared can be replaced by that. I'm going to do that first. Is this just one page? It is one page. Okay. So I'm going to rewrite as secant squared t dt over the square root of 1 plus tangent t. So you already noticed that dy is in the problem, so this is the square root. I'm sorry, the integral from dy divided by the square root of y, which is good enough. Because this becomes the integral from y to negative 1/2 dy, which works just fine. What function prime is y to negative 1/2? And the answer is to negative 1/2 plus 1, which is 1/2 indeed, divided by 1/2 plus a constant c. In other words, to the square root. Oh, plus c. But I have to go back and replace it. And what was y?
1 plus tan t.
That's it. Not too difficult to go back and check.
So plus C or minus C?
There is never plus or minus. There is always plus. I just wrote the equal symbol, my mistake. Sorry. My mistake. Any questions?
Seems like it could be some trial and error sometimes.
I wouldn't say trial and error. I would say sometimes
Well, I mean,
there is a better substitution than
right, the way I did cosine squared t, we would have figured out maybe it wasn't the right thing.
I would have never started with cosine squared, because cosine squared doesn't bother me. 1 plus tangent under the square root bothers me,
Okay.
because I can't simplify it.
Would we have got the same answer if we had used the square root of 1?
Of course, absolutely. Let's try it. So now we would like to use y equals the square root of 1 plus tangent t. If it works, if the substitution is the right one, yes, the answer will be the same. So then dy equals 1 over 2 the square root of 1 plus tangent t dt. So please always remember the difference between y prime and dy. So dy is the differential, f prime of x dx. And y prime is the derivative of y. I don't want the derivative. I want the differential of y.
Right.
Okay. So then coming back to our problem, I'm sorry, multiply by secant squared t dt. I jumped. Right? So 1 over 2 the square root times the inner function prime. I talk too much. That's me. Sorry about that. Okay. So now here's our integral. So the integral from secant squared dt over the square root of 1 plus tangent t. I'm missing the 2, no problem. I'm dividing and multiplying by 2.
Okay.
So this is 2, the integral from y dy. Right? So this is this with dt.
Yeah.
I don't even have the y, actually. That's the whole thing. So 1 secant squared over 2, yep,
Equal to what?
yes, it's 1. 1. What function prime is 1? No.
C to 0, y.
Yes. 2y plus a constant c, of course. So this is 2 the square of 1 plus tangent t plus a constant c. The derivative of y is 1. The derivative of 1, it would be 0. Good. Has to be the same. So in certain situations, we may have 2 or more possibilities that will take us to the same target. 2 or more starting points that will take us to the same target. In other situations, there is only 1. And we have to find that one. Any questions? Any questions? Okay, let's choose before we look at definite integrals using a substitution. Anything else?
Can you move the paper down?
Yes.
I think I got it.
What about 40? Same page, 414. So here's 40. The integral from sine x dx, everything divided by 1 plus cosine squared. Now, what would you like to get rid of? 1 plus cosine squared. This is what I would like to get rid of. Okay. Now, if I choose 1 plus cosine squared as the substitution, I will get into a little bit of a trouble. But let's see what happens, right? So if I say let y be 1 plus cosine squared x, I will have some difficulty because dy equals 2 cosine x times negative sine x dx. It's not going to work because I don't have a way of creating negative 2, which is fine. Negative 2 is okay, but I don't have a way of creating sine x cosine x dx. And I'm not going to multiply top and bottom by cosine because I'll get into more trouble. So it happens that this is not the right way for this one. Still the focus is on cosine, on the denominator, but not on 1 plus cosine squared and not on cosine squared. But on what? Nope, I can't. There is no such thing. I don't have anything that is 1 over cosine squared here. Just cosine. Because dy will be negative sine x dx, and that's not a problem to make the negative. Multiplying by negative 1 twice. I do have this, which is very good. And this will become very good. So this is negative, the integral from dy over 1 plus y squared. This I know. And there exists a function whose derivative is 1 over 1 plus y squared. Yes? I have to copy this. Very good. Very good, awesome. It is indeed arctangent y, because arctangent y prime is 1 over 1 plus y squared. I have to go back to the original variable. So this will be negative. I have to replace y by cosine x. So this is arctangent applied to cosine x plus a constant c. It's okay to try. It's okay to say, yeah, I would really like to get rid of 1 plus cosine squared. And it's okay to say, uh-oh, it's not working because I can't make up this cosine in here. I can make up a number. I can make up a sign. So a factor or a sign, that's okay. But an entire function, no, most probably. Very good. Okay, what about 44? Any questions on this problem? In 44, the integral from x over 1 plus x to the fourth dx. And then I would like you to choose 46 or 48, because they look interesting. Maybe 48. Okay. Yes, pretty similar to the previous one. I would really like to get rid of 1 plus x to the fourth. However, it's not going to work. But it's okay to try. So I'm going to say y equals 1 plus x to the fourth, but dy will be 4x to the third dx. And I get in trouble. I can make up 4x. I mean, the 4 I can, but x cubed I can't. Exactly. X squared is the key. Very good. Yes. I'm going to say let y be x squared. Exactly. Why? Because dy is 2x dx. X dx I have. I'm missing your 2. It's not a big deal. I can multiply top and bottom by 2 anytime. It's not going to make any difference. Multiply the top by 2, I multiply the bottom by 2. I'm not changing anything. But this is correct. And this is very good. Very good. Awesome. So this will equal, so from here I'm jumping here. It's 1/2 in front, and you already told me dy over 1 plus y squared. We already know what this means. It's 1/2 arctangent y plus a constant c. However, I have to go back and plug it in. I have to give the answer. I have to give the answer in the variable that was the integral was, or the function was given. Did we get the idea of the substitution rule for indefinite integrals? Yes? Okay, let's also look at 48. Before we look at indefinite integrals, we're using the substitution rule. So that is the integral from x cubed, the square root of x squared plus 1 dx. Okay, now before we do this, the sophisticated notation, and you will understand immediately, is the integral from f of g of x times g prime dx. But this is what we're doing. We're choosing the function, and we are determining g prime dx, which is the differential dy. That's exactly what we're doing to get f of u du or f of y dy. That's exactly what it is. But this is the sophisticated notation. Okay, so let's go back to our problem. Okay, what do you think? This doesn't bother me. The square root doesn't bother me, but this does. So this is my starting point. If I say let y or u, the book uses u, use any letter you want other than x. You can use t, you can use y, you can use u, whatever you want. So x squared plus 1, then dy is 2x dx. Now I have to think for a moment before I say no, it's not working. So this will become, if I'm on the right track, this will become the square root of y. We agree on that. Now, one of these three x's with a 2, 1x, 1x, and dx, this, and only one of these will become dy. Now, what is left over? Correct. Can I, from here, determine x squared? The answer is yes. How much is x squared from here?
-1 x 1. Or what?
So although this is slightly more sophisticated, I can still make it work. Correct. So let's start from scratch. So the integral is x cubed, the square root of x squared plus 1 dx. So in a square root, I really don't want to have a sum or a difference. Because if I have a sum or a difference under the square root, there is nothing I can simplify it with. The square root of a sum cannot be simplified. So I'm hoping that I can get rid of what's under the square root. So just for every now and then, let's use also the notation from the book. So they say they don't like y, they like u. Fine. I'm going to say let u, bless you, be x squared plus 1. But I'm on the right track if du is in the problem, because otherwise I won't be able to make it up. So du equals 2x dx. Agreed? So I don't have the 2, but remember, a constant will never create a problem. If it's -1 or 1500, it doesn't matter. I can multiply and divide by 1500.
So would it become 1/2 crazy f du times square root of y?
So it would be this. 2x times x squared times the square root of x squared plus 1 and dx. Have I changed anything? The answer is no. Instead of x cubed, I have x times x squared. Is that okay? Instead of 1, I have 1/2 times 2. So this is still the original integral. Agreed? Okay. Now, if we are on the right track, then this piece with this piece will form.
dA y.
Yeah, this time we're using u. Good. We're using u. I just used the notation from the book. Instead of y, I said let u instead of y. You can use y. It's not the same thing. It doesn't matter. Is this okay?
I don't know.
Okay, so we denoted this quantity, x squared plus 1, by u. We determine the differential of u. Is that okay so far?
Yeah.
Which is 2x dx. Is this okay?
Yep.
Then I realized that I really needed a 2 in there. So I multiplied by 2 and divided by 2. This product is still 1. 1/2 times 2 is still 1. And I rearranged x cubed as x and x squared. Is that okay? So now 2x dx, these three pieces form du. Now 1/2 is outside. What is this piece?
Square root of u.
Very good. So now the question is, because once I move to x, I can't have x and u in the same
U
integral.
-1 squared.
Exactly. This piece becomes u minus 1. No, without the square. So x squared
Oh, that's right.
is u minus 1. And now I have all pieces accounted for. They're all changed into u. There's no more x. Is this okay? Caesar, is this okay?
Yeah.
So I have 1/2 in front, and then I have the integral from u minus 1, the square root of u du. And you can say, what did you accomplish with this? A lot. Because first of all, now I can distribute this, and I have 1/2, the integral from u to 3/2 minus u to 1/2 du, which is a piece of cake. So this is u to 1/2 multiplied by u, copy the base, add the exponents. And this is u to 1/2 times -1, which is negative u to 1/2. And this is not a difficult step. So I have 1/2 outside. And this is u to 3/2 plus 1 over 3/2 plus 1 minus u to 1/2 plus 1 over 1/2 plus 1 plus a constant c. Yes, I have to simplify those pieces. And I have to go back and replace u by Perfect. Thank you. So 3 over 2 plus 2 over 2 is 5 over 2, and I have to flip. So 1 over 2 times 2 over 5 multiplied by u to 5/3. I'm sorry, 5/2. Then again, minus 1/2. This is 3 over 2, so it's 2 over 3 times u to 3 over 2 plus a constant c. I take care of the numbers in front, 1/5, and now u is x squared plus 1 to 5/2. Take care of the numbers in front, 1/3, x squared plus 1 to 3/2 plus a constant c. Yes, this required several steps. It was not a trivial situation. And it would have been somewhat difficult to guess it without the substitution. Okay, do we need more examples on the indefinite before we look at definite? Moving on to definite? Okay. Remember, every time we calculate the definite integral, what do we have to check? That the function is continuous on the given interval. Otherwise, we cannot use the fundamental theorem of calculus part 2. Okay. Ready? Let me choose a couple and then feel free to choose, okay? Say it again? Yes. Yes. So we're looking at problems 53 through 73. Still on page 414. I don't particularly like any of them, but let's start with 71. The integral. Yes, yes, because they have limits of integration, yes. I'm going to change z to x because my z is not that. So it's e to x plus 1 over e to x plus x over times dx. Okay. Prefer y or u, it doesn't matter, or t. Okay. Let y be. What do you think? E to the x is friendly.
E to the x plus x.
E to the x plus x is not friendly, and because it's in the denominator. Correct. E to the x plus x. Only if dy is in the problem. Not enough? Good. Good. So then, this piece is perfect. This piece is good. Please do not copy anything. Stop. Stop. Be careful. Stop, because it's a definite integral. The integral from, just give me the function. Very good. Because we moved from x to y, we cannot copy the limits of integration anymore. So, careful. When x is 0, what will y equal to? So for the lower limit of 0, for x equals 0, how much is y? Careful. 1 plus 0. Good. When x is 1, how much is y? E plus 1. Very good. You cannot copy or change an integral from x to an integral in y and still copy the limits of integration for x. Because you have to determine new limits of integration for the new variable that you created. This was not necessary in indefinite integrals. Why? Because that was a function, and all we had to do at the very end is replace the substitution. Go back and replace y by whatever we denoted. Whatever expression we denoted by y or u or whatever. But here, we don't want to go back. Because the answer will be a number. It doesn't matter if I calculate it in terms of x or it's calculate in terms of y, it will be the same number, whatever it is. We don't want to go back. And we cannot continue copying the same limits. I saw some students do that, and they go back and then change x into x, and then they still, no, that's not correct. Okay, so now, which function prime?
Work if you went back.
Yes, I don't recommend it. Yes. You can consider it as being an indefinite integral and then change it at the very end, go back to x, and then keep the same limits of integration. I don't recommend it. You may forget, you may plug in, who knows. So in the definite integrals, please, once you change the integral from x into the new variable, also change the limits of integration, and you do not have to go back. Just move forward. Okay, so then now, what function prime is 1 over y? Perfect. So this should be natural log of the absolute value of y plus a constant c. I jumped again. We're talking about indefinite. That's no need, not needed anymore. From 1 to e plus 1. This is an indefinite. This is a definite integral. Yes.
Why is it the absolute value?
Very good. Very good question.
Because it's from the point.
No. Nope.
Oh.
Okay. So the integral from 1 over x dx, this is natural log of the absolute value of x plus a constant c. And now I need to convince you that when I differentiate this side and differentiate this side, I get the same thing. Okay, so now it's clear that when I differentiate the constant, I get 0, but I want to show you this, correct? So the absolute value of x, let's start with the absolute value of x first. What are the options for the absolute value of x?
1 over x, 1 over negative x.
Careful. Just the absolute value. No differentiation yet.
X or negative x.
Awesome. Agreed with this? Okay. Now I would like to discuss this. So it's natural log x. Why am I writing? And I hope you agree, I can no longer keep the 0 in there, right? Or, so far so good?
Yeah.
Okay, now I want to differentiate this. So when I differentiate the natural log of the absolute value, I will differentiate this, and I get,
1 over x. When x is big.
and when I differentiate this,
1 over negative x.
times the inner function prime,
Negative x.
Times negative.
Negative 6.
so they are the same. And we have to put the absolute value. Every time we integrate 1 over x dx, the answer is not natural log x, but is the natural log of the absolute value of x. And that takes care of it. And of course, the function doesn't exist at 0. Its derivative will not exist at 0. But because when we differentiate the inner function, so when we have this, natural log of negative x prime is 1 over negative x times the inner function prime, we obtain the same answer. So that's why we always have to put the absolute value. Now, if the limits of integration are between 10 and 15, I don't need to put the absolute value, because natural log of 15 minus natural log of 10, both are natural log. But if I have the integral from negative 15 to negative 13, then I have to put the absolute value. Okay, so coming back to our problem. So I have to plug in e plus 1. There is no need to put the absolute value on e plus 1 because it's a positive number, minus, when I plug in 1, natural log 1 is
0.
That's it. We cannot simplify this in any way, shape, or form. There is no property of natural log of a sum. We have 3 properties for log. Log applied to a product, to a ratio, and to a power. This cannot be simplified in any way. Okay, let's choose another, and then I'll let you choose anything you want.
Well,
Yes? That's it?
how does it become e to the x?
What do you mean by e to the x?
Well, we have
E to the x is gone. We forgot about it. It's done. We changed the limits of integration. We are not going back.
once you change, so you don't have to go back to the 0
Once I change the limits of integration, the number will be the same.
already.
You can go back to x. I don't recommend it.
Hmm.
You're just going to make your life more difficult
All right.
in going back. Once you change the limits of integration, then you're done. You're solving the integral in
So-
terms of y now.
So where did the minus 0 come from?
The fundamental theorem of calculus part 2 says natural log of this minus natural log of this.
Okay.
F of the upper minus f of the lower. But f of the lower is 0.
But.
Yes?
Question, though,
Yes.
why was e to the x plus x?
I don't care. It's gone. This is my new integral with new limits of integration. What I had before, I don't care. I'm not going back. In a definite integral, the answer is a number. I don't care how I solve it. If I solve it for x or I solve it for y, the number will be the same.
Okay, so then what did you substitute for y then?
I don't care. The integral is the integral from 1 to e plus 1 from this. I don't care what I had past that, before that. This is my integral.
Okay.
And the answer is this. Does it make sense?
Yeah, I mean, it makes sense now. 'Cause I thought we were having to.
If
go
you
back
want to
and-
change y back to x, then you have to change the limits of the integration back to the limits of integration of x, and you'll still get the same answer. But I recommend don't look back in the indefinite integrals. Once you move to the new integral with a new variable and new limits of integration, what you had before, because then the answer is a number. And if you're solving the integral in terms of x or in terms of y, the number will be the same. The final answer will be identical. Okay, this was just the first example. Let's look at a few more, and you'll see what happens. I mean, it's the same idea. If you have any preference, let me choose one more. Let me choose one more, and then whatever you prefer.
Yeah, that makes sense.
Say it again.
So you showed us one thing and then it was another thing.
No, they are two different things.
Yeah.
One of them is indefinite, in which you have to go back and replace. There is no other way. The final answer is a function, and it has to be in the variable given in the original function.
Right.
If the integral is given in x, you have to end with x. And the second one is indefinite. The second one is definite, and the answer is a number. I don't care if it's based on y, x, z, t, w. It's one number, and I'm not going back.
Okay.
Can you? Yes, you can if you want to. But I think there is no need. You already have a simpler integral than you had before. Why go back? Just to find a number from a more complicated expression? There is no need. But for the indefinite, you have no choice. You have to plug in the substitution at the end. Okay, so let's take a look at something else. Like, for example, 60. The integral from 0 to 1 from x e to negative x squared dx. And I forgot on the previous integral to ask you, and I should have, and I said it at first, but I forgot to ask you, is this function defined continuous between 0 and 1?
Yes.
Because when you plug in, so see, I have to make sure that e to the x plus x is never 0 on this interval. So e to the x is always a positive number, and I'm adding, so it's a positive number, never 0, and I'm adding a number between 0 and 1. So it can never be 0. Good. As long as you make sure always that the integral, that the function is continuous on that given interval. Okay, very good. So now, what would you like to make disappear? Yes. So I want this. Only if dy is in the problem. Is dy in the problem? Negative 2x dx. Negative 2 is friendly. There is never a problem with negative 2. Multiply and divide by negative 2 is a piece of cake. And now I have this, which represents dy indeed. And I have this, which represents, good. Do not write the limits of integration, please. So this is e to y dy. You understand why I will never want to go back?
Yeah.
So now, but now the limits of integration have to be corresponding to or in reference to y, not to x. So, of course I did. Thank you. Thank you. Sorry, my apologies. So when x is 0, how much is y? The lower limit. When x is 1, good. So we have a negative 1/2 in front.
Say that you determine the upper.
When x is 0, y is 0. When x is 1, y is negative 1. Better?
But you don't want to flip it, correct?
I will talk about that in a minute. There is no need. So, what function prime is e to y?
E to y.
From 0 to negative 1. I don't recommend going back because you complicate things. You're going back to a complicated expression or complicated function versus this. So, negative 1/2, plug in negative 1, and minus when you plug in 0. Very good, awesome. So this is negative 1/2, 1 over e minus 1. Or negative 1 over 2e plus 1/2.
So
Yes?
why are you plugging in negative 1 and not 0?
So I found the antiderivative. Fundamental theorem of calculus part 2 says, in the antiderivative, plug in the upper limit first and subtract when you plug in the lower limit. So negative 1/2 stays outside. When I plug in the upper limit, I get this, minus when I plug in the lower limit, I get 1. Should I write this? Let me write it here for you. So the integral from f of x dx from a to b is f of x from a to b, or f of b minus f of a. This is fundamental theorem of calculus part 2. And this is what we are using here. Is that better?
Yes.
Now, is it clear why I don't want to go back to the previous variable? Because I want to handle e to y. I don't want to handle negative or 2 or x e to negative x squared dx, bless you. Right? Does it make sense? Is that a yes? Yes.
Bring it down a little bit. All right.
Yes?
Plugging in the zeros, how she got the -1.
I know that. I don't understand how that becomes f of b minus f of a.
So this is the antiderivative, which is here. So now I have to plug in b to find f of b. When I plug in negative 1, I get e to negative 1. And then I copy minus. And I plug in 0. E to 0 is 1 to get f of a. So this is f of a. This is f of b.
Okay.
Better?
Yes.
Very good. Let's look at another. Yes, what about 68? The integral from 0 to 4, x divided by the square root of 1 plus 2x dx. Is this function continuous on 0 to 4? Yeah, because 1 plus 2x has to be strictly greater than 0, and 2x greater than -1, and x greater than -1/2, and this is greater than -1/2. So the function is continuous between 0 and 4. Okay, so what would you recommend we do?
One plus 2x.
Okay, perfect. So let y be 1 plus 2x. dy equals not sufficient, not very good. I don't have a problem with 2. So this will turn out to be indeed. So I'm not afraid of that. This will be I have to make up an x. No problem. How do I make up this? Exactly. So subtract 1 and divide by 2. X equals y minus 1 over 2. So this piece is this. So then 1/2 is outside. The limits of integration, please. When x is 0, how much is y? When x is 4, how much is y? Do we agree that 0 for when x is between 0 and 4, y will be between 1 and 9? Very good. So I replace this x by y minus 1 over 2. I replace this by dy. And I replace this by the square root of y. In the denominator, of course. So this one is in the numerator as y minus 1 over 2. This one is in the denominator. And then I have dy. It needs work. But I can separate it, and I'm going to move 1/2 in front. I don't need it. It's a factor. I want it out of the way. So then y divided by the square root of y is y to 1/2 minus 1 divided by the square root of y is y to -1/2 dy. So what I did, I'm sure you understood this. So y minus 1 over the square root of y is y over the square root of y minus 1 over the square root of y. This is crucial to understand. And this is power 1. Power 1 minus power 1/2 is power 1/2. And this is y to -1/2. And again, indefinite integrals, we're not going back. Don't you complicate things if you do. So this is 1/4. Which function prime is this? So it's y to 1/2 plus 1 over 1/2 plus 1 minus y to -1/2 plus 1 over -1/2 plus 1. It's a definite integral from 1 to 9. Any questions? I know it's not done. Any questions? I will clean it up a little bit more with these fractions in here, and then plug in 9, and then subtract when I plug in 1. Agreed? 1/4 can wait, so this is 2/3. When I plug in 9, I have the square root of 9, which is 3, and 3 cubed is 27. Minus 2, the square root of 9 is 3. Minus. Parentheses, so I don't forget to distribute. Very important. When I plug in 1, 2/3. When I plug in 1, minus 2. Let's take a moment and think about this. So I flip this into 2/3, and when I plug in 9 is the square root of 9, which is 3, but cubed. I flipped and I get 2. The square root of 9 is 3. Minus, when I plug in 1, 2/3 minus 2. And I have to perform these operations. So it's 1/4 outside. This is 18 minus 6 minus 2/3 and plus 2. 1/4. So this is 12, 14 minus 2/3, or 1/4. How much is 42 minus 2? And then 10/3. Okay, now feel free to choose anything you want.